right, as many of you know, this is Donald Becker, and his talk is going to be how Linux conquered supercomputing.
Okay. Up there is my list of a partial list of all of the things I used to be known as, starting back at MIT, where for many years that was a valid email address, but none of those email addresses outlasted any of those jobs, which is a frustrating thing, including, I would say, some of the history has been erased because when you make the mistake of being tied to a place like that, and they all, and you sort of agree, they own all of your correspondence in a sense, but you should really always own your correspondence so you don't walk away not having any record of everything you communicated with people. But part of that's my own fault for not having kept my own archive and make sure that my archive was not commingled with things that would be erased at the last second. Anyway, yeah, I was at MIT. I was at the IDA Supercomputing Research Center where I started working on Linux. At NASA, at Goddard Space Flight Center, where we started the Beowulf Project, and it became the big thing that it was. It also enabled me at both of those places to be a contributor without, especially at NASA, I was working for a research center and negotiated that I would own the copyright on my code. And by I meant that the whole world would be able to make use of my code, not that I would be walking away with the copyright. And that was actually a challenging thing at the time to negotiate something that worked for everybody and wouldn't be bounced back or complained about. Still was, but that's a different story. Okay, so I'm going to start my disrobing. You know, one of the things we were always trying to do is make software that just sucked just a little bit less than the one that came before. And that in part was our tagline. But the real point of the job, and this is a lot of people's favorite thing, Penguin Computing. I was CTO of Penguin Computing for a bunch of years. I had this as a mouse pad and a t-shirt, and we always joked about total world domination with Linux and with other places like, I'll be your server today. Or the one that said, scientists predict someday the sun will fail, but your Linux systems will still be running. And nobody would have taken that as anything but, yeah, bravado, that will never happen. Sun will be there forever, and Linux will go away. And where are we today? Total world domination, just like we promised all those years ago. Anybody doubt the total world domination? Still not desktop.
I don't doubt it, but for years, Linus only used one slide in his talks, which is a straight line graph of where Linux stuff would be. And then one day he pointed out it was on a logarithmic wire code, right? So it was actually an exponential growth.
And yeah, we actually won years ago in supercomputing. I think long before people realized that Linux was the dominant operating system at the high end, it actually was. It had won somewhere between 98 and 2003, the breakpoint had been reached. In 1993 is when the Supercomputing Top 500 list was created. In 1993, 0% Linux. In 1993, I built my first set of machines connected together. I was already a contributor to the Linux kernel. We were putting in the first real TCP/IP stack. And I say the first real TCP/IP stack because I'm going to give credit to a program called KA9Q, which was intended as a user-level MS-DOS TCP/IP stack that somebody had done a good job of making it run at the kernel level, but it was just really low performance. It existed before I started working on it. It showed that it could be done, but it was not suitable. So there was actually a networking stack before I started working on Linux. But by 93, we had a real TCP/IP stack in Linux. We had converted to one. Ross Bureau and I. Ross Bureau at Stanford. Most people forget his name, but he was the other key person in getting Linux networking started at the very beginning. And between the two of us, we got an in-kernel TCP/IP stack that performed, was entirely functional, I'll put it that way. In 1993, I started connecting machines together, and I wanted to build a compute cluster. A little bit of background there. I was working at the IDA Supercomputing Research Center. That's NSA captive research. We were semi-academic. And one of the little things I did was actually got the first open source software released through the NSA as in an official way. It took 6 months. That's why there are still little parts of the kernel from back then that said copyright assigned to Dernza, director NSA. So little tiny thing, took a whole bunch of time, completely unacceptable path for releasing source code. And they was a lot of paperwork on everybody's part to make that happen. That was part of the reason I moved over to NASA, had that extra A to the name. You could talk with everybody in the world without sending reports to start the Beowulf Project. So in 1993, 0% Linux, but we were just starting to build scalable computers. And in 1994, I went over to try to make that a reality, to build high-performance machines using Linux and clustering. And from there, we had huge success. 1996, we did a machine on the floor at Supercomputing conference, which was just about to change its name. And in 1997, we got the Gordon Bell Prize for Price Performance, and that was a key public acknowledgement that we had finally reached the point where this was viable for high-performance computing. Right about that time, nobody was saying supercomputing anymore. The supercomputing name slipped off to the side. The conference became named as SC and not supercomputing. And from then on, we always talked about high-performance computing. So we got the Gordon Bell Prize with a team of us working across the country, Caltech, Los Alamos, some really smart guys who were doing gravitational n-body simulations, which used to be the exclusive domain of vector supercomputers. One of the characteristics of gravitational n-body is that every body, if it's heavy enough, impacts the orbit of another one. No matter how far away it is, if you're massive, you still have that influence. So it means it's an all-to-all problem. These guys demonstrated that no matter how hard the problem looks, you can break it up into sub-groupings that you can compute locally and not have to communicate all-to-all. And they took a really hard problem that people thought, well, you always need a vector machine for that, and made it so we could map it to a cluster of machines. Independent machines communicating over Ethernet. And that is the kind of multiple level of we built machines from scratch, we got the operating system to work, we tuned the networking, we got new applications, new ways of structuring applications, scientists who validated them and put the whole thing together and demonstrated we could solve supercomputing level problems with these, little consumer PCs that nobody thought was worth anything, that were far more cost effective than it was being built at the time. That was the breakthrough, and things proceeded from there to 2003. Probably a year or two before that was actually half Linux on the top 500 list. And that's an amazing thing to go from nothing to more than half and rapidly increasing and the fastest machines in the world. Linux had dominated, it was total world domination. And somewhere between 2016 and this year's list, where we're certainly at 100%, the top 500 list of the 500 fastest publicly acknowledged machines in the world all run Linux. Total world domination. And make sure I got, so, first picture I put up, I wanted to, this is a machine you've probably never heard of. This is Small cluster built in 1995, but it is an example of how it was the community, was a bunch of different people working, wouldn't say anonymously, because in the academic world it's got a few papers written about it, trained a lot of students on it. They were the first external cluster where we taught them how to build. Here's our recipe, you go off and make one, and let us know how it goes, and we're going to come out and help you, we're going to fix everything, we're going to make it so you can do research on that machine. So George Mason University, Tarek El-Ghazawi, professor there with one of his students, and it was a picture I pulled out from my own collection that he had sent me. And you would probably not find this on the web. You search for Beowulf cluster, you search for anything, you don't find a picture like this. You find the people who were promoting like we did it first, but these guys were actually, oh yeah, we're gonna build a Beowulf cluster of our own. They weren't first, second, 10th, somewhere around that. They did a lot of the hard grunt work of, yeah, this is a new concept, we're gonna try it out, we're gonna teach students how to do it. That's what made it succeed. Now we got the high profile things from later machines where you see room full of machines stacked up, and this is actually at NIH, I think this is Beowulf, or the first Beowulf system, where they were building increasingly large clusters. That was key as well. People were going off and using the recipe, and some of our software, some of the software they developed their own. The recipes we provided, they added things to build increasingly gigantic clusters. The picture on the left there is actually the second Beowulf cluster we built at Goddard, and that is when it was delivered to the Computer History Museum. So they're actually, I believe, both of the first machines have at least parts in the Computer History Museum now. Yeah, so I've already been talking a little bit. You have a rough idea of who I am, but there are a lot of people who, it was a long time ago. I was the guy who started the NASA Beowulf Project. I was the one who wanted that to happen. Thomas Sterling went out and rounded up some of the money. Jim Fisher was the project manager who managed to make that happen. Jim Fisher was famous in high performance supercomputing in the 70s and early 80s, working on some massively parallel machines. He was a program manager at NASA, and he was a great guy because he managed to defend all of the money. It takes a long time to get money, and Tom Sterling managed to do that at NASA headquarters. But more importantly, over the years, people will steal your money. And if you don't want to spend all your time defending your project and making sure that the money that was stolen gets stolen back, you need people like Jim Fisher who made sure that happened. So a lot of credit to people like that who, I didn't think of it much at the time, but made sure that all of that continued. So at the NASA Beowulf Project, our goal was to not just build a sample machine, a machine we could write a paper about and say, look how good it was. It was to build, document, educate people, and build a community around how to do scalable clustering. And that was because I had the experience of contributing to the Linux kernel. I was a major kernel developer at the time. I saw how powerful it was, and I absorbed that lesson without even thinking that I was observing the lesson. We're communicating with everybody all over the world. We're working with people simultaneously from every major place that had people just building their own Linux machines. We built a community, not an operating system kernel or an operating system distribution. We were building people a way of working together. And that's the thing that made all of this succeed. I wrote a huge amount of code, but the code and my direct contribution to writing the code is minuscule compared to all of the other people who contributed. And I wrote a whole bunch of code that you'll never see ever again because it was ad hoc, not good enough. Somebody wrote something better. That community is what ended up being the success, not how much code I could write. 16 or 18 hours a day at a keyboard. As I said, I did the part of the first real networking stack for Linux, giving credit to the people who had put in K9Q. And I quickly moved down to the queuing level, the performance level, the device driver level, making sure all that worked. And I effectively did all of the networking device drivers and some of the infrastructure for supporting that through about 2001. And the reason for that is around 2000, all the vendors discovered, oh, we can't let somebody else write our driver. We have to do it. We're not going to tell them what, we're not going to give them data sheets. We're not going to let them do it. We're going to do it ourselves, so we have that in-house. Linux had become important enough that I was thankfully effectively put out of a job. Yes. Because I was running mailing lists, I was running the Beowulf Project, I was doing a whole bunch of things all simultaneously. And besides that, I've been a long-term contributor. I think I was going to bring this slide up to that. You know, we were talking before in the room here just a few minutes ago, Linux, I only cared about networking performance and some I/O performance. But for me, I wanted the fastest networking, the lowest latency networking to put in there. And we achieved that in the 1990s. We were the fastest operating system on PCs out there. I wrote almost all the device drivers for networking. I made sure that they were all common, that they all worked exactly the same way. And spent a long time tuning and restructuring the system so that we could be cache aware on as many processor types as possible. And that paid off because we beat almost, I would say we beat every other operating system out there. So, Ted,
Yeah,
why don't you tell your little part of the story there?
sure. So I'm from the Bay Area, and worked in Japan for a company called Adaptec in SCSI and Ethernet 10100 adapters in the 90s. I came back and at Adaptec in Milpitas, everyone was talking about, well, 10100, what's next, you know? And we were diddling around with ATM25 and ATM155, which were specialized for telco. But the word going around in Silicon Valley in 94, 95 was gig Ethernet. And we knew people at, like the third guy at Sun started a gig Ethernet basic company called, and left Sun, called Granite. And at Adaptec, we decided we're not going to do our own silicon. We're going to see what Cisco does and what this guy Granite does. So, anyways, there was another guy named Bernard Daines who had done the first 10100. So Bob, 3Com guy, Bob, can't remember his last name, is known for doing like Ethernet 10, and then Ethernet 100 or fast Ethernet. Bernard Daines did at a company called Tidewater in Union City. He made a lot of money with Cisco after selling that and another company to Cisco, and he moved back to his hometown of Spokane and started a company called Packet Engines, saying we're going to do the first gigabit Ethernet NICs because Granite was acquired by Cisco for $100 or a couple $100 million. They didn't want to do NICs; they were mainly boxes. So they continued with that box, and then Bernard Daines and Packet Engines said we're going to do NICs, and so we did ISA NICs, and then we did ESA NICs, and we did SGI NICs and S-Bus Sun NICs. But we had trouble with drivers. So around 96 or something, we realized everyone wanting to buy NICs were every national lab, Los Alamos, international ones like CERN, LIGO in Washington, Argonne. And so we dedicated a salesperson named Kim Stearns to track these down. And they were all buying NICs, you know, they're like $2,000. And they're all saying, you know, we want Linux. We don't want these S-Bus drivers for Sun or these SGI drivers or whatever, these Windows NT version that we want Linux. So Kim tracked down Donald through the Beowulf list starting, and we brought Donald up to Spokane for a week, and within 1 week,
Was I don't think I even ended up going there, did I?
you did. You came to Spokane, and yeah.
I wasn't getting a lot of sleep in those years, so I did not actually remember.
But he had a driver called the Tulip. I think it was based on the DEC 10100, 2150, or 154.
It was.
Yeah, and he modified that to Hamachi.c, which you can still find the code if you Google it. And he wrote that in a week, or he finished it based on it. We were scared because we had to give him our data sheets to our ASIC. So if he had a friend who worked at a foundry, we're giving all our IP away. And later we sold the IP to 3 companies like NEC, Intel, and Cisco. So it was multi-million dollars we were trusting him with. But he made that work, helped us exit for, I don't know, $500 million to Alcatel a couple of years later. So everyone at Packet Engines who, you know, made enough stock money to buy a car, a house, 50 people became millionaires, owe Donald for that. And the rest is history.
So from my perspective, this was just another card, but it was gigabit Ethernet, and we were all, so I did the channel bonding, which was aggregating multiple channels together, which by the way, I found out later from various patent office calls and questions that we had innovated a whole bunch of things with a whole bunch of approaches to joining network channels together. Other people went right away and patented them. For me, it was like, oh, we need to do this. We need 3 network channels because we're running, you know, we don't have enough bandwidth, especially with 100 megabit a second. We'll just aggregate them. We'll do all the different ways of aggregating them, see which ones work for latency. And latency was a big issue, out of order arrival of packets with high bandwidth, all those issues. But so gigabit Ethernet card comes out, advertised in the market. Looks like you can buy it. They haven't got a price. They've got here's where you order it. I want to get a sample, and it's like, oh yeah, we can get you a sample. And it just like weeks and a month or two. Yeah, we can get you the data sheet. It took a while. It's like, they're selling these to everybody. Why can't they get me one? And then I get one, and I think it's, you know, serial number like 3 or something. So one of the lessons learned is all the vendors lie about having something. They basically market it, say, oh yeah, we've sold millions of them. Oh, you've got 1 million orders. We'll put it in there. We'll start fabricating them now. But yeah, within a few weeks, we had, I believe, triple Microsoft's networking performance numbers because while we hadn't had gigabit Ethernet to stress the system, what we had done was basically cache-aware networking. We completely wiped everybody else out of performance with that because one of my focuses was performance of networking. And again, I don't care about the rest of what's going on. I care about networking performance. And there were the SCSI guys and the subsystem, disk subsystem guys. They didn't care about networking. They cared about disk I/O performance, and they did an awesome job. So it was everybody working together that made this an operating system that, in retrospect, we were going to win because we had the performance advantage. That was one of the reasons. And in those years, I was doing a whole bunch of other things: diagnostic support programs, infrastructure, tools, all sorts of things inside supporting the Linux kernel. I think I wrote, I estimate about 100 device drivers in those years. About half of those were networking device drivers directly. I did a PCMCA, then a card bus subsystem support, just so I could get those network cards working. I did a partial USB stack, just so I could get the USB networking adapters working. And then as soon as somebody else was willing to do a real USB stack that supported everything, I was happy to abandon mine. But yeah, a lot of contributions in those days. So I'll go back a little bit of prehistory of what I worked on. I used BSD Unix 4.2, 4.1 on the back system. I had access to the source code. Great system, learned a lot from it. I was at MIT doing that. I influenced heavily by And it's one of those things where you don't realize you're being influenced, but the Free Software Foundation was what it ended up being called. People working on free software after having the painful experience of developing software for free and then being commercialized and they can no longer use their own software. A really heavy influence on picking the right license, drafting the right license, making sure that you don't screw yourself over in the future. Back then, I was actually the guy who did the third port of GCC to the well-remembered Fairchild Clipper architecture. Has anybody ever heard of that? Fairchild made a Clipper RISC processor. Yeah, you're the only one in the entire world who remembers that. So I was actually a compiler guy way back when. And I wrote a user-level read-write NFS server for the multiprocessor I was working on at the time, a research multiprocessor, just to support that. And didn't think, I put that out in the world, didn't think anything of it until years later. Where I actually started using Linux was because I was doing a global inlining version of GCC as a project that ended up going nowhere, but we were going to inline RTL. Functionally it worked, but marketing in the sense of getting it to the rest of the world didn't pan out. But my itch was wanting to access my housemate's unused disk space. And I actually had to buy my own machine because if I wanted my code to go from the inside to the outside, that would never happen. It had to be done on an outside machine. If I need to work on an outside machine, I waited to work on my machine I bought. And I didn't want to spend as much money on the Unix as I did on the hardware. So started using Linux just to run GCC, just to compile GCC. And then because GCC was gigantic at the time, I lusted after my housemate's disk space. He wasn't using that disk. It had lots of blank sectors. I needed those sectors. And that is actually the reason why I started working on the Linux networking code, was just to get access to his remote access to his NFS server on the desk on his Sun workstation. So, little side thing there. But here's the important part of the talk. We won total world domination. Why did we win? I can look back now after all these years and pick out a few key things, and they weren't technical. They won because we were a little smarter, we had a community, and we did it the right way. And people can take these lessons going forward. It wasn't a butterfly flap. It turned into a tsunami. It was being a little bit better than everybody else. And one of the ways was the low entry barrier. And everybody should look at this for their project. The kernel supported both low and high-end hardware. And that really dropped the entry barrier. It supported many more pieces of cheap hardware. And you went to any of the other Unix clones at the time, they would only support one SCSI adapter at one particular mapped location, or maybe two. I think there was the Adaptec SCSI adapter, but it had to be exactly the way the developer machine was. And it had to be that relatively expensive card. If you didn't care about disk performance and you wanted an IDE drive, you're not going to be running that. Linux supported the cheapest drives out of the box, the cheapest mice, the cheapest video cards, and the high-end ones for performance too, if you needed that. But if you wanted to just use the very cheapest, they supported that as well, and nobody else did that. So the entry cost was low. The distributions were superior. You could just put in a bunch of floppies. The Texas A&M had a distribution that made it super easy compared to everything else. And that continued with when I started writing device drivers. We did innovative things, probing for devices. Does anybody here remember how it used to be a real pain in the ass to set up a PC? You would jumper things.
Not just painful, but painful!
You would need to know all the hardware details. You would jumper it, you would look it up, you would enter like it's coming in an IRQ whatever, IRQ2, IRQ5. You had to know which ones you couldn't use and which ones would work best and how it worked with your motherboard, and then enter it in a text file on the machine, and you had to get it right or it wouldn't work, and it wouldn't tell you why it didn't work. One of the things, I'll pat myself in the back, some other Linux developers were already starting to use probes. They would look for their device, and if it was there, they'd say, sweet. If it wasn't there, it would be like, ignore it. And I took that pretty much to the limit. I looked for every device driver on the ISA bus would look for every possible location or every reasonable location for the bus. You could override it if you needed to, but almost all the time it would find the device. And I went further. I developed auto IRQ, which was, put an interrupt handler on every possible IRQ, trigger an interrupt, see where it came in on. Super simple technique. Nobody had been doing it to that point. Or though, actually, there was some start of that idea, so I won't take full credit for that one, but nobody was doing auto DMA, which was the same thing with the DMA channels. If you use DMA, trigger DMA, look to see which DMA channel was used, that's your DMA channel. Almost always worked. More importantly, it worked way more often than people entering it manually. It was part of ease of use. So we went to extreme effort, and that all paid off, because when you're doing clustering and you have 50, 100, or 1,000 machines, some of them are going to be a little different. You can't configure it. You might be network booting them. You want them to all just work. And when you're supporting your own software, your own device drivers, your own kernel, every time something doesn't work, you're the one getting the email. And if you hope to remain sane, you have to make it as easy, painless, and foolproof as possible. So we got to jump by being easier, just flat out being easier to use, low-end hardware, automatically configuring, look to see what you had. So it wasn't just the dice roll, it actually was better. It helps every user, and it especially helped when we were doing clustering. But an early edge can be lost. Linux had that edge in the beginning. It was a little bit behind the other BSDs, but in retrospect, not that far behind. We had the edge in usability. Where we kept that edge and succeeded was constant focus on performance and reliability. Today, it doesn't matter as much, but back then, the uptime of your machine was an indicator of how stable it was. You had a kernel uptime that could run for 2 years. Well, first of all, you were beating Microsoft because they would always crash, 40 days or 80 days?
I think it's 26 days. It's because of an integer overrun.
On the clock, yeah. And nobody ever ran it for long enough to correlate that, that was going to crash your machine. Because if you managed to run it that long, it was going to crash, but you never managed to run it that long that you could say, oh, it always crashes after this.
I don't only think that's true. It might be folklore, but I think it's right.
Yeah, and it was actually true, and then it was not exactly true in later Windows kernels, but it was a story that was basically nobody expected Windows to be reliable. Everybody expected Linux to run, and if you could keep your machine up for a year while you were pretty out of date, and you really, really needed to update, but it was cool that you could show an uptime of literally over a year. And our model of the world has completely changed since then, but uptime we thought that would be the key feature for doing high performance machines. If you have 1,000 machines and one crashes every few days, that would be a crisis. Today, that's not actually a crisis. And the other thing is, Linux had the model. I would call it absurdly parallel bug reporting and fixing. I personally ran a whole slew of mailing list for every network driver that was significant, every major network driver, and a bug reporting separate mailing list for every major driver. So anybody who was interested could be on that mailing list, or more importantly, look at the mailing list archive. All the other developers were doing the same thing at the same time. You could report a bug, somebody would see it in hours, a whole bunch of people would see it immediately, and that would be fixed by whoever knew how to fix it at the time, and nobody else was coming close to that kind of bug turnaround time. We didn't do that intentionally, it was just the way it worked out. We had a bug fix turnaround time that was, in retrospect, absolutely astonishing. And I already talked a little bit about domain features. What I care about, performance, network performance, and then secondarily, CPU performance. I could care about that. I could make sure my tuning, all the code for mine did a really good job with that, and I could make those changes. Everybody else who cared about their subsystem could make their changes, and it all worked together. We absolutely won. And bottom line here, it was the community, it was all of the people working together that made this happen. Even people who didn't write code, who contributed bugs. By the way, I don't think there was ever, approximately there was never a bug report with a chunk of code to fix it that was correct. But the fact that I got the bug report, and like this is pretty much where the bug is, if you've changed this section of code, that's probably where the fix is, that's hugely helpful. And having all those people to bug things for you wouldn't have been possible without that. And here's another thing that you should do a takeaway here. Don't forget the license. The license, GPL isn't perfect, but it's better than almost everything out there. Start that with that as your idea and maybe figure out a better license. But so many projects have made the mistake of, especially the BSDs, and I'll point those out. Many of you didn't live, maybe not even alive at the time, but people would, I'll characterize it as, they'll look at this giant highway. Their goal is to build 10 feet of road so they can put up a toll booth and sell it to people to take ownership of all of the value. And they could because it was the wrong license. They could make one change, they could fix one bug and say, mine is better than theirs. It doesn't have this bug, and I'm gonna charge you the full value. And that happened again and again with lots of open source projects, especially the BSDs. Or the other equivalent approach is you build a wonderful branch highway to an exclusive resort where you collect all of the revenue, but you're not adding value to anybody. You built that highway, but it's just to your stuff. But I always have the perspective of you need to work with the infrastructure, you need to work with businesses. Don't make it so it can't be commercialized, but try to protect yourself against somebody stealing all of the value and removing it from the community. There's no way that I can give you advice on how to do that properly, but always keep in mind that you have a trade-off there. And if we had gone down the path of BSDs, none of us would be in the room here today. And I'm running out of time, so I'll make this the final thing. A long-term perspective on winning. We absolutely did win. We dominate supercomputing. We dominate the high end of computing. If you're running a cloud, you're running Linux or Linux with something else. If you're running a data center or a web server, it's probably Linux. We never expected to be here saying, yeah, we absolutely won. But part of winning is, you have to start out with the idea that maybe you won't completely win, but you at least, you can influence the way other people build their systems. You can set the baseline of you have to be at least this tall, or you shouldn't even be releasing your commercial software. You can force others to improve. And in the beginning, that's originally what I thought we would be doing. It's like, if you can't beat Linux kernel developed by hobbyists, some quite professional hobbyists, some people in their early teens, if you can't beat us, you shouldn't be in the game. Because some of us are quite skilled, some of us don't have the experience, but a lot of drive. But we're not being paid directly to do this. You can't beat us, you shouldn't even play. No, we're not that good. We were actually that good and way better than everybody else. But at the time, it was like, we're amateurs, you should be able to beat us, and you can't. So I expected that would be the influence we would have. We wouldn't directly win, but we would make the world better because we would force other people to be better. The real lesson here is persisting success only comes when you build a community. Because at some point you will burn out, and the harder you You work, the longer the days and as the decades roll on, at some point you will not be able to maintain the thing you created. You always have to be spreading it out, making a community. Some other people are going to get a lot of the credit for it. And by the way, that'll be my final point here. You know, Beowulf succeeded because we had Beowulf.org, a website I created, but it's in other people's hands. The Beowulf Bash, which was a community gathering we put together at the Supercomputing conference every year. Other people run that, and it succeeds because there are a whole bunch of people working hard, spreading the ideas, working together without it being a central single person to do it. And finally, well, on this slide, it's always getting harder. You might feel you can't make a contribution because things today way more complex. I could do the third port of GCC in the 1986 or 1987 because GCC was tiny compared to the way it is today. And you might think, oh, you could never have an influence, but people are the same today as they were before. You can pick something up like that and make a big difference. Don't be daunted because it's way more complex than it was easy for me because I could actually understand a big chunk of the system that'd be impossible today. It's the same way for everybody. You might think, you know, at best I can influence the world, but you can influence the world. You can make somebody else be better. And you might be surprised that your system, the thing you're building or the community you're putting together, that doesn't just make other people try a little harder to win. You might actually end up being the winner. And finally, on a personal note, you know, failure is an orphan. Success has many fathers. You'll have to accept that when you go out and something succeeds, you won't get all the credit you think that, you know, you were the first to do this. Well, other people did it a few months later. They're effectively the first as well. That's just the way. People aren't going to give you credit for everything you did. Accept that up front, and you'll have to have personal, you get that personal feeling of success. My name's over a lot of things. I didn't always get credit for everything, but I got plenty of credit in the end. And that's all that matters. You made the world a better place. You know, you bent it to your will in a sense. And it's the people who go out and envision what the world's going to be and say, you know, we'll make that world. We're not just going to passively let it evolve. You can affect how the future of computers, you know, how they're built, how they're put together, the future of software, the future of collaboration. And every era we're going to have another crisis of, will this be a private company-run thing, or will this be a community standard that everybody can gain value from? And you can make sure that every generation we still have a big community standard aspect of it. And run way over my time, but we still have time for questions because Mad Dog doesn't talk until 2:30, right?
First of all, you can take your time. Second of all, you have another T-shirt to show them.
I actually brought one of the things I can dig deep into my T-shirt archive. At one point, I had over 100. I'm not going to keep stripping down. I want to wear these, but this is Extreme Linux, the first CD distribution for high-performance computing. Before I started my company, which did clustering distribution, we put this out in conjunction with Bob Young at Red Hat. Bob Young personally pushed it. It was an Extreme Linux distribution. We use this logo. Apparently that's a collector's distribution that not everybody used, but this logo, who was the one who developed this logo, Mad Dog?
Bill Pridgeon was the one who did it. I suggested the actual thing and it's hot and it's cool, but he did the drawing. He did some of the original Tux drawings for the Linux Journal way back when. So lives close to Portland, Oregon now.
And let's see, which conference was this? This is the annual Linux Showcase. but we had several t-shirts for cluster-specific conferences with the same logo on. So this is a little historic logo, and Mad Dog went out and remade the tattoos that we had from back then. These permanent tattoos. So anybody who wants one or a few, Mad Dog had them made up, so they're up here. I can pass them out, and we'll have some time for some questions here.
There's no directions on them, but you wet down your skin first, put the tattoo over, and then use a damp cloth to wet the back through and through, and then peel off the back, and you got a tattoo. That'll last for a couple of weeks, but then you use baby oil to take it off. That's it.
I still had a few of these original ones in my memorabilia collection, so this is reproduction vintage.
Those will apply to most plastics. You put the
Oh, it'll go to
temporary
plastics too?
tattoo on most plastics, it'll treat it as a sticker. It'll last.
That'll be, that's cool.
Yeah.
Yeah, well, my first job out of high school was working in an ISP, and I've used a lot of your code. It turns out I saw your name a number of times. Do I remember on the tap ton when you mod probe that when it prints your name out?
Which,
The ton tap?
the tunnel one, or was it? So there were a bunch of things that were both tunneling and parallel port IP and things that were non-traditional network devices. I originally used my name and my personal email address so that people would know where to send bugs to. Eventually I wised up to my name and then the mailing list that you should send the bug to, not my personal email address, because it was useful to be able to sort out. It would still come to me, but I was getting hundreds, sometimes up to 1,000 pieces of email a day that from all the mailing lists and everything, but it was way better to be able to sort them beforehand so that everything didn't come. But yeah, one of the reasons I became known, and I think everybody, all the major developers should have done this, is you put your name down so that when people send the bug reports, they just look at, oh yeah, that device driver loaded with that version and that person, and that reporting email is right there, and they're gonna get a bug report because it just crashed. They didn't have to look very far, but it did mean that a lot of people saw my name as scrolled by.
Yes, well, thank you for your service. I
Yeah.
used a lot of it.